I thought I would start by maybe the most outstanding example in this direction of linear programming. So linear programming, it's a whole area. It's linear algebra with inequalities. That's what it really is about. And the whole area just sprang into existence after World War II, or in the developments of World War II. I guess the most famous name in linear programming is Danzig, who created this Simplex method. Pretty unusual for a method to survive fundamentally unchanged for such a long time, that the first method suggested to solve linear programs should turn out to have such a long life and still very alive, with competition now from a different class of methods. But I hope you'll feel that this subject is kind of fun. I'm picking linear programming. Well, I'm just creating an example here to show what duality is about. And then the second lecture this afternoon, please stay for part of it if possible. It's about some integer programming problems, like the marriage problem. Marriage usually have an integer number of marriages. And in fact, this problem is highly moral. You have either 0 or 1 marriages, and how many are possible, and so on. And the network flow problem, maximal flow problem. So that's the second lecture. This will be linear algebra, as I said. Let me see what's the primal problem? The unknown is x. So we minimize the cost, which is C transpose x. You see the linearity. The cost depends linearly. x1 up to xn might be the amounts of n different materials that we have to buy. And C's would be the costs the unit costs of those materials. So if we buy n materials in these amounts at these costs, that's our total cost. What are the constraints? The constraints are one. Here's the key constraint: is that the vector x, all the components have to be non-negative. We can't use negative amounts of materials. And the other constraint is that we have to satisfy some requirements. And those will be expressed by ax equal b. So there you go. Here's our friend ax equal b appearing again. And now notice with m with few equations. So hopefully many solutions. We're expecting lots of solutions if we have more unknowns than equations. But we're, of course, looking for non-negative solutions. Well, then the question is, are there any? That's already a question. Are there any vectors x that solve the constraints? This is called feasible. If an x that satisfies the constraints is called feasible. Feasible x. And then among the feasible x's, we're looking to minimize the cost. So that used the inputs A, B, and C. And it's pretty straightforward. You can see the type of problem that comes in. The cost is linear, the constraints are linear, and there's this inequality constraint. Okay, now I want to talk about the dual problem. And the point is that throughout this subject of optimization, there's a twin problem that uses the same inputs A, B, C in what looks a completely different way. And yet their two are closely related. This is one of the more subtle aspects of linear programming and all of optimization, is this presence of dual variables. Well, actually, that theme of variables x's and y's has been fundamental in this whole, from the start of these lectures. You remember in our network flow problems, we had potentials U and currents W, and there was a certain duality between those. And in fact, we had N potentials and M currents, N nodes and M edges. Oh, actually, graphs with nodes and edges are going to be central in the second lecture today. So it's not totally news to us that there's some reverse problem, which turns out to be a maximization, also a linear problem, of course, and now it'll be the B transpose Y. So the B that was in the constraint is now popping into the cost, if I call this cost, or whatever, income maybe. And what are the constraints on this? Well, not to anybody's surprise, A transpose is going to show up. And this vector C is going to show up on the right-hand side. So it'll be A transpose Y equals C. Okay, have I got that right, or do I want greater than or equal? I bet I want greater than or equal. I better just check. Do I want less or equal or greater or equal? I think I want less or equal, because, not surprisingly, we had a greater than or equal in the primal problem. Well, less or equal shows up here, but the main point is A transpose shows up again. So we really, I could stretch our little framework. Why do I say little? Our framework of 3 steps to include linear programming. Shall I do that? And then, well, so let me make some comments about this and do that. Yeah.
How are the x's and y's?
Well, at the moment, these are 2 independent problems. I could hide the dual problem, never tell you about it, and just discuss the primal, how to solve that. I am revealing that there's a second problem, which if I had 5 lectures on linear programming, I probably wouldn't reveal so early, that there's a second problem hiding around with the same inputs, and also another linear program. That's a linear programming problem too. Linear programming is linear costs, linear equality, and inequality constraints. However, I can massage one problem to fit another one. I could have AX less or equal B there and play with it and introduce some slack unknowns to make up the equality sign, and they would have to be non-negative and add them to the x's. All I want to say is that this fits the general form, but others that don't look like they quite fit do, as long as they have linear costs and linear equations and inequalities. Yeah. No condition on y. Yeah, it's interesting. That's why you saw me goof and correct. I have to think every time. Okay, is there a condition? Let me tell you about duality. So duality. So I'm really jumping here to the heart of the underlying math. Says that the maximum in the dual problem equals the minimum in the primal. That the answer to this problem, the maximum whatever, is equal to the minimum cost. So that in a way this is a big help, because it tells us when to stop. If we have suppose we have an algorithm that gradually finds better and better x's. This is what you really do in reality. You get a approximate x and you say, is that the best I can do? You look around it, as calculus always does. You say, oh, I can go off, I can change that x to reduce the cost, and so you go that way, and then you don't know when to stop. Well, there's several ways to know when to stop. One is when you get to a point, x star, let's say, let's call y star the winner here, and x star the winner here. So I'll sort of introduce the notation star for the optimizer, the best. Then, so one way to stop is to get to some x star. You don't know that it's x star yet. You look around, but every way you look is worse. Yes, yeah. This is the minimum cost. So I mean that at the this says this quantity that you're trying to maximize when you do it equals this quantity that in this other problem you're trying to minimize. Well, you're naturally asking yourself, what's the relation between these problems? So let me prove right away weak duality. What's always easy in these problems is to show that the maximum is always below the minimum. Maximum in one problem. That looks goofy, right? Max less or equal min. But this is the maximum in the dual is always less or equal to minimum in the primal. We can show that right off the bat just from taking two steps will do it. But those are different problems, so not too surprising. And then the serious duality thing is that actually, when you push this quantity you're trying to maximize as high as it'll go, and you pull this quantity you're trying to minimize, this cost down as low as it'll go, they meet. And then you know you've got the answer, because they can't pass each other according to this simple. Let me just prove that. So the maximum in the dual for any. So this, take any x. I want to show that this quantity C transpose x is. I want to show that C transpose x is always less or equal B transpose y for any allowable x this is for any allowable x and y. So no, yes, maybe no, maybe yes. Let's see. What is it? I just got them reversed here. The thing I'm maximizing, right? Thank you. The thing I'm maximizing. Sorry. Take that off the videotape. Okay, B is B transpose y. That's the quantity that I'm maximizing. So I push that up, but it doesn't matter. Any y that's acceptable will be below in the cost of any x that's acceptable. Thanks. And now that's for any acceptable, any, shall I use the right word, feasible x and y. Any feasible x and y. This will work. Okay? Can we just take that step? Let's see. If y is feasible, then let's see. Ax is b, right? If x is feasible, ax is b, right? So I know that. So now I'm going to connect those problems. If x is feasible, then ax is b. So this is ax transpose y, right? Because b is ax. Okay? Now what am I going to do? Well, anytime I see ax transpose, like one idea in my head, write it as x transpose, move the parentheses, write it as X transpose A transpose Y, and move the parentheses so that I'm looking at A transpose. Was that A transpose? What did I have there? Y. Yes, I did. Thanks. Okay. That's the key step. So simple for matrices, corresponds to integration by parts in continuum problems that we met for a while. Okay, and now why is this? So that's okay, right? Actually, was that an even and equal? No, that was right. Okay. Oh, that was even and equal sign, wasn't it? That was even and equal sign because AX was exactly B. Okay, now I'm ready for the step that this is less or equal this. Now, why is that? Because A transpose Y, you don't mind what order this inner product comes in. Those are just two vectors. I'm happy to write X transpose C if you would like. Let me write it there as X transpose C, which is the same as C transpose X. It's just the dot product doesn't matter. Okay, here's the key step then, obviously. And why is that true? Well, first of all, A transpose Y, it's beautiful how all the requirements come in. A transpose Y is less or equal to C. So does that make this true right away if A transpose Y is less or equal to C? Not right away. I need to know that I'm multiplying this inequality A transpose Y less or equal to C by positive numbers. If you take an inequality you multiply by a negative number, it reverses it. But that's exactly where this comes in. So, and in a way, yeah, more than in a way, here we can see, is that all right? So that any feasible one was less or equal, any feasible Y gave a B transpose Y that was smaller than or equal to C transpose X. Now our point is that, so that's the easy step. I mean, right? That just, and there was a corresponding easy step when we were doing minimizing potential energy. There was something called a complementary energy that involved the flows, or the stresses, whatever that dual variable was, and we could have found a weak duality, and then ultimately equality. So I proved, like, you'll see that often to prove this, that in one direction it's easy. That's the direction we took, but now to get equality is not so easy. But actually, when would equality hold? So now this actually not only gives us an easy argument, but also gives us a condition for optimality. When are these equal? Since we have all equal sign, I only have to ask right there. It's when they're equal, I guess. X transpose. But when will equality hold? X transpose times, now I'm just going to put them on the same side of the equation, times C minus A transpose Y has to be what? Well, right. It's always greater or equal 0 from feasibility, but to get equality, so this is to get equality, equal sign, to be optimal. So that was an important word in there, optimality. That meant, what's the condition like derivative equals 0 in this world? Well, it's just that this has to be equal 0, right? I'm just looking at the only place there was any question and saying, if we want equality, then we got to have equality at that step. So this less or equal followed immediately for any x and y. Equality is only going to happen at the best ones. So maybe I should put the star, x star transpose, c minus a transpose y star. That's how we recognize the winner. And you see what's going on here? This is a dot product of two vectors. And what's the deal with those vectors? What do we know about those vectors? Well, they're orthogonal, but then each of those vectors is non-negative. The x is non-negative, and the c minus a transpose y is non-negative. So, when could two non-negative vectors be orthogonal? If I have a couple of vectors, there's some sort of a complementary condition. If x is actually positive, then if a particular component of x is actually positive, then the ith component of this guy has to be 0. And similarly, if our A transpose y is strictly below c on some component, then the corresponding x has to be 0. It's really neat stuff. In a way, these x's are like Lagrange multipliers for these, and somehow this business of this is somehow it's, well, I don't know what words to use. There's this, but this is a typical feature showing up in linear programming that connects the x's and the y's at the winner. So what I'm doing so far is pure algebra, right? I've asked you now for these minutes to just accept these two problems, the primal and the dual, as announced. Then to verify that sure enough, by accepting those, we got weak duality, and then identify the one place where equality has to hold to get duality. I haven't given you any help up to now with examples, so it's time for me to turn to an example. So you see what kind of questions these are. So I'm, these last four lectures are really coming back from the Applied Math book, Introduction to Applied Math, Chapter 7. Chapter 7. 7 and 8, really, is where the last lectures are going to come from. And including the marriage problem and the other special network problems that are following this afternoon. But for an example, I'm going to turn to my linear algebra book so that you have a sort of independent example. This is one where, so now I'm going to this example. So can I describe the example? And you'll see it and then see it as a linear programming problem. Okay. So so the problem is 4 homework problems. Oh, if I write that up there, you won't realize this is example. This isn't the homework. These are not the homework. I'm not going to say the homework problems. This is just, there are 4 imaginary homework problems at minimum cost. Okay. So what are the rules? We've got 3 x's. So x1 is the work done by a PhD on these problems. x2 is the number of hours spent by a grad student. And x3 will be the number of hours spent on the problem by a computer. Okay. So we can solve these problems by any combination of number of hours. So now I have to tell you how much those cost. And actually, I used numbers that were unrealistically small. But let's stay with them. So the cost is $5 an hour for the PhD, $3 an hour. Well, that's unrealistically large, most grad students would say. And $8 an hour for the computer. Okay. And then, how fast can they solve the problems is another question. The PhD can solve one problem per hour. This guy is equally fast, one problem per hour, and the computer is twice as fast. It can solve two problems per hour. Okay. Okay, now I've told you everything about the primal problem. And can we state it as a linear program? So what's the cost? Total cost is, so we minimized the cost, which is what? Well, this is $5 an hour for x1 hours. And the grad student it costs $3 an hour for x2 hours. And the computer costs $8 an hour for x3 hours. Good. So our cost is linear. And that's linear cost is quite reasonable. You know, we're assuming then no efficiency of scale, right? If we had 100 problems, the computer might be able to, you know, we could write a better program and solve them more efficiently, or even the grad student might speed up or slow down or whatever. But right now, linear. Okay. What's the constraint? Well, the constraints are that they can't work a negative number of hours and interfere here. So x1, x2, and x3 are all greater or equal to 0, right? Okay, but now what's the constraint about getting the 4 problems solved? All right, C. So I just want to get 4 problems solved. So if this person works for x1 hours and is able to solve 1 problem per hour, I think here's the constraint, that x1 plus x2 plus 2 x3s is 4. So this is the number of problems solved. This is an equation of the number of problems solved. So this one works x1 hours, solves 1 problem per hour, total x1 problems, x2 problems. The computer works x3 hours, but because it solves 2 problems an hour, the number of problems it solves in x3 hours is 2x3. Is that okay? So that our matrix then has only 1 row. It's the matrix 1, 1, 2. M is 1. One constraint, and n is 3. And you're not allowed to solve the problem on the fly here. You have to listen to linear programming as we go. Okay. It fits this framework that first of all, there are many, many solutions. Many, many feasible points. Feasible point is a vector x that's non-negative, required, and that satisfies the one equation. So we got 3 x's. Let me draw the feasible set. So this is coming from Introduction to Applied Math. And here's a picture of the feasible set. This is x1 direction, this is the x2 direction, this is the x3 direction, and I'm sort of imagining the positive octant. Do you too? So what is that? What's that equation give me in my picture? if I graph the points that solve that equation, I get a plane. I get a plane. That's a linear equation, gives me a plane. So that plane, of course, goes infinitely far. I mean, regular plane. But I'm only allowed to look at the part of the plane that's in this positive octant. So I'm seeing sort of a plane that, well, actually we could figure out what these corners are. You see, this is the plane. This plane is there, but we're only keeping the part that's feasible, right? We're only keeping the points that are. So what is this point here? That's the point x1 equal 4, right? Yeah, x1 is 4, and the other x's are 0. So that's the point x, if I wrote it as a vector, 4, 0, 0. That's a corner. Maybe I call that corner P. And what's this corner Q? This is the point, also 4, so it would be the point 0, 4, 0, where all 4 problems are being solved by the grad student. And then this point up here, say R, has coordinates 0, 0, because it's, and then 2, because then the computer would work 2 hours. Now, and any mixture. In between, the triangle in between is any mixture where they're all working. Well, the point is that I'm looking for the x star now. The best, the cheapest. Who should do this work here? And the point will be that one of these corners is the winner. That if I, and I'll think why, but let me emphasize that point. The winner is at a corner. The winner is at a corner. So let me think. So what does that mean in ordinary words? That means that the winner, only one of these x's at the optimal x star is working, is not 0. And I only need like one x to adjust because I only have one equation. So a corner, let me sort of say what a corner is. Corner is, I have m non-zero x's, and that gives me enough to solve the m equations ax equal b. And the n minus m 0 x's. Because I'm at a corner. So we can visualize this thing in this 3D picture. The visualization gets quite harder in m and n dimensions. So my point was that the winner, x star, is a corner, some corner. But the thing is, so you might think, okay, just try all the corners. Evaluate the cost at every corner once you know the winner is a corner. But the thing is, there are too many corners. The number of corners is n choose m or something, which is a very big number fast. It's 3 here. So there are 3 corners, and we can check them all. But generally, you have to imagine, so are you imagining n-dimensional space like this, where n was 3? And then what do the constraints give us? So think of n-dimensional space, x1 to xn, and then we have m equations. The m equations, what do they give in this space? Well, every equation is linear, so it's a plane. So I've got m planes, and so I've got this octant, I've got this octant positive direction in n-dimensional space. I don't know why I'm saying this because I can't visualize it either. But except it's sort of important to realize that the feasible set is a polyhedron. It hasn't got any curved boundaries. Everything is either they're the base planes, which chop out the coming from x greater or equal 0, chop out the positive part, or the constraint planes coming from the m constraints that cut through in some way. So you got somehow a region that's created out of m plus n planes. But it's can be quite complicated. If m plus n is a pretty big number, you're say we have, this wouldn't be big, 20 equations, 10 constraints. So we're in 20-dimensional space. We've got 30 planes all woofing through. And you can see that the feasible set could be empty. For example, how could I change this how could I create a problem where there were no feasible x's out of this example? Well, I could make that 4 a minus 4. If I made that 4 a minus 4, then there wouldn't be any non-negative x's that would solve with a minus 4. But of course, the problem with minus 4 homeworks to do, well, often I have no homeworks, but I never assign negative number of homework problems. So anyway, okay, which is the winner? Which is the best point? Well, in this case, I could just check the cost at every corner, right? And I have to say, why is the winner at a corner? The fact that the winner is at a corner is a big help. And it somehow depends on linearity. You know, if we have a linear function, if it's increasing, it continues to increase until you bump up against the constraint, or continues to decrease. If we're trying to make something decrease, like suppose you said, well, maybe that's the winner in the middle there, all three working away. Well, but if I discover that to move from there in some direction is better, then more is better, more is better, more is better, until finally, maybe I just make it hit an edge. At that point, it can't go, it's not legal to go further because an x would get negative. So at that point, I look again. Okay, but now my point is that we only have to consider corners. And why is that?
Suppose you could restrict that to one of the edges, and it's the same reason we get.
That's right. Drive to a corner. That's the fundamental reasoning. Yeah. One way to see it is now to think of these costs. If we got so this is a good way to see it, not only that it's at a corner, but what picks out that corner. So the cost, suppose I'm trying to do this job for a total cost of $1 million. It's not going to cost me $1 million for these very parsimonious workers and only 4 homework problems. But suppose I look at the equation 5x1 plus 3x2 plus 8x3. Oh, I don't even know if I could spend $1 million. Yes, I could. Could I? I don't even know. But anyway, suppose I look at the x's that that give me a cost of $1 million. Yeah, I don't think I could spend $1 million. They're not feasible, right?
If you think of it, that is another plane.
Yes, exactly. That's what I want to do. That's right.
You hit a corner.
Exactly. Right. So if I tried to spend $1 million, that would, if I look at the equation, the plane, 5x1 plus 3x2 plus 8x3 equals $1 million. That's off here somewhere. Well, okay, I'll reduce that. Let's see, what am I trying to do? Minimum cost? Why don't I start at 0 and move up? That'd be smarter, right? Okay. So let me take the plane equals 0. That's a plane, right? It's through the origin, but I don't think it would touch the feasible set. I can't get my problem solved for 0, right? I mean, somebody's going to have to work and get paid here. Yeah, so this plane would, like, are you imagining this as kind of it's a plane now. It's not a tetrahedron. That's just a plane. And this plane would lie somewhere behind it, not touching. But then, as Bob says, if I increase this to 1, it'll move up. It'll move parallel to itself, of course, because I'm just changing the right-hand side. But it's still, I can't get them solved for $1. Up to $2 and so on. The plane is moving. You see this plane, this cost plane, sort of moving toward the feasible set, but not touching it at $2. There's nobody, I can't do it for $2. And then finally it touches the feasible set. And of course it touches at a corner. That's the minimum cost. So the cost is, I can't do it for cost 0, I can't do it for cost 1, I can't do it for cost 2. I move that plane up, and then finally I can do it. And a plane moving forward will hit a polyhedron at a corner. That's the geometric way to visualize the reason why the winner is a corner. So I just...
What about the one, like, if it's moving parallel, if the plane is parallel to one face?
Oh, what would happen? Then it could hit the whole thing, right?
Right, it'll hit the whole face.
Right. So that would mean that any of these plans would work. So if I adjusted these costs to be 1, 1, and 2, exactly, you're picking out a degenerate case. That if the PhD and grad student charge $1 an hour and the computer $2 an hour, and they solve them exactly in proportion to their cost, which would be imaginable, then, as you say, this plane would be parallel to this, and it would, boom, it would hit the whole feasible set all at once. And that would mean that in that degenerate case, not only are the corners winners, but even everything in between. But still it's true that the winner is a corner. Well, but not the only winner. Yeah, yeah. So it's a line. So, yeah, it's like I mean, we're dealing with linear equations here. It's like that case would be like, you know, optimize when you're what's the maximum of that horizontal function? Well, the maximum is whatever that height is, but it's satisfied at it's all the points are just as good. So, but of course you know that that's a special case. So typically, when planes move parallel to themselves, they'll hit a corner first. But there would be degenerate cases where it could hit a whole edge at once, or even the whole flat face at once. So that, yeah. So there are degenerate cases always possible. Just like the feasible set might be empty. There might be nobody that solves the equation if I had a -4 here, but I don't. Yeah. So this will be a perfectly non-degenerate, completely normal case of linear programming. And let's see, I was going to emphasize it. So who uses linear programming? Management. I mean, this is like a major application of mathematics in management planning, management science, I guess is the right description. So there's but also in our science, the big requirement is the linearity here, and of course lots of problems are not linear, and then we have to escape from those requirements. Maybe I mentioned, what is quadratic programming? What is quadratic programming? Quadratic programming, I'll include a quadratic factor like x transpose kx in the cost. So then I'm minimizing a quadratic subject to linear equations and constraints. So that's a case of quadratic programming, much closer to the rest of this course. If I throw away those constraints, then I'm right at the rest of this course. Minimizing a quadratic with linear constraints is exactly what we might have minimize that energy subject to Kirchhoff's current law or something like that, the subject to the balance equation. So this is that. This is the next step after linear programming would be quadratic programming, and there would be a dual for that too, and it would be another quadratic program. But the real starting point here is linear programming, and then that simplifies the theory because we know the winner's at a corner. Okay, now which corner does win? The grad student, right? Because the three corners are, I could figure out the cost. Here are the PhDs doing all the work, solving all 4 problems, working 4 hours for $20. Here the grad student is doing all the work, working 4 hours, $3 an hour for 12. Here the computer is doing all the work, only has to work 2 hours, but its cost is $8 an hour, so this is $16 also. So 16, is that right? Yeah. 16, 20, or 12, so the winner is, the optimum is there, the grad student. All right. Now, but this was a small problem where we could check all the corners. And my point was, can't do that usually. So now I speak about the Simplex method, which starts at some corner. I need some preliminary method to find a corner. Suppose I start at corner P. So start. And the idea of the Simplex method will be to move to another corner, a neighboring corner. What's a neighboring corner on one of these high dimensional deals? A neighboring corner means one of the x's becomes one of the x's that was 0. Well, look, here you go. Here's the x at this corner. What happens if I move to that corner? This x, some x drops to 0, and some other x enters. You could say x1 leaves the basis, is when I travel up here, and x3 rather, enters the basis. I'm using that word basis pretty freely. x1 leaves the solution, becomes 0, and a different one, x3, enters the solution, becomes non-zero. And the cost is reduced. Went from $20 down to 16. Okay, then I look around from this corner. Which way shall I go? I go along an edge to the next corner. So I could go along this edge or along this edge. So I compute which way is the best way to go. Well, when I go this way, my computations are going to show I'm worse. It costs more. When I go this way, it costs less. I'm reducing the cost. So, of course, I'll go that way until I can't go any further because I'm reducing. The more work the grad student does, the more work that's taken away from the computer and given to the grad student, much cheaper, the more, as I travel down here, I'm giving more and more work to the grad student until I reach that point when I can't take away any more work from the computer. The computer is no longer doing anything. It's dropped to 0. So in this case, the entering variable was the grad student, number 2. And the leaving variable was the computer, number 3, and it left to the point of dropping to 0. The grad student moved up from 0 to something, whatever something it took to satisfy the constraint, and I am at a new corner. Now I look around from that corner, and the simplex method, of course, doesn't know it's got to x star, so it would look around, it would say, there are 2 ways I can move from here, but they both mean a cost increase, so I must be at the winner. So that's the idea of the simplex method. Start somewhere, start at some corner, travel along edges, reducing the cost every time, until you get to an edge where the cost cannot be reduced, and then that's x star, the winner. So that's the simplex method. Now I have to tell you how the simplex method chooses the edge to travel on, right? Because in a big problem, I'll be at a corner, whole bunch of edges, a whole bunch of possible entering variables, a whole bunch of x's that are willing to work. And the simplex, and some of those will mean higher costs, so I won't go those ways. And some will mean lower costs, so I will pick out which way to go, which new x should enter. And then I have to go along that edge until I come to that corner, to that next corner, and then I do it again. So that's the algorithm. Repeatedly, you're at a corner, you test directions, you travel on the direction where the steepest descent, the cost goes down fastest per step along that edge, and then you get to the next corner and you do it again. Is that a picture of, yeah? How do you know that you're not just at a local minimum? Very good question. It's because of this linearity. From these linear equations and linear constraints, you can't get in trapped. But and similarly, if I had this quadratic one and was positive definite, I couldn't get trapped. But absolutely, local minima and so on are the they're the big challenge in minimization problems in general. You give me a function, a cost function. See, most cost functions aren't linear. You give me a cost function of f of 100 variables that you allow me to play with, and how do you minimize a function of 100 variables? Boy, that's the zillion-dollar question. And if that function is convex, then so if the function is shaped like this, maybe with wiggles but still convex, then you know there's only one minimum, and the problem is much easier. If the function is quite general, it can have loops like a golf course. Its graph is some surface with ups and downs and ups and downs. Then when you find a local minimum, you can't just look around in a local minimum because everything looks upwards. But at some other point, there's a thing much further down, and a whole lot of ideas have gone in to this subject, and I guess there are a lot more to come, because you somehow have to jog that possible local minimum, enough to get out of that little well and on with the job. But how much do you jog by? And you don't want, if you spend all your time worrying about this, you won't find that local minimum in the first place. It's fascinating. Now, okay, one comment here, and I wasn't planning and don't have time to develop interior point methods, but just so you could guess what that means. That means that we travel in the interior. We find a point. So interior is interior of this feasible set. Find some place that solves the equation don't worry about the number of zeros and non-zeros. This had to do with corners. Find a point. Find a direction is better. Travel in it. Decide when to stop, and probably stop short of the boundary. Then you're still inside. Calculus still operates, so to speak. Look around, find another point, travel for a while, find another point, and eventually, in infinite many steps, reach the winner. I mean, because you're always stopping short, but getting closer and closer. But of course, in reality, we are happy to get within 10 to the minus something of the winner, and that's okay too. So that's iterative, and this is a finite algorithm, right? Can't take, well, we know it's finite because the darn thing has only a finite number of corners, finite number of edges, and we're not going to go backwards on an edge because, as we saw, if we went forward on an edge, that was because it improved the cost, reduced the cost, and we'll never travel backward on that edge. So it's got to be finite. But the number of edges is exponentially large for M and N, and so there's a big, the theory of the simplex method is, does it actually take exponentially long as M and N increases, or can it be done in polynomial time? This is the most important problem, where it was quite unclear, even to experts, whether it can be done in polynomial time, meaning a power of M and N, or whether it grows like the number of corners, which is n choose m and grows exponentially. Well, here's the answer to a quick report on that. The simplex method can, in really hooked up cases, take exponentially long. So if I describe the simplex, the clear, straightforward simplex method, although its average cost, and it's used all the time, so of course it doesn't take exponentially long, or we wouldn't use it. But its worst cost, in an extreme example, could be exponential. We could travel along exponential number of edges before we finally settled on the winner. And you see, because traveling on an edge, the computing cost is the same, however long the edge. So anyway, but average costs are polynomial. So a lot of people, and a guy at MIT is looking at this problem again and found another way of describing average costs and showing that that's polynomial. And then there is a polynomial algorithm for linear programming. You have to twist the simplex method to make it polynomial, but you can do it. So there is a polynomial algorithm, but most people are happy with the simplex method, which is polynomial in all practical cases. So this is polynomial. Actually, this is polynomial too, in getting getting within a given epsilon in polynomial time. Can I mention the name of the guy who, Guy Carmarker, who proposed, he threw a bombshell into this well-established theory by discovering a method for which he claimed high efficiency. So he's, in his presentation of his new method, it was beating the simplex method, which, there is a serious revolution in an important scientific subject, because these calculations are done a lot. Then, well, much more, of course, that led to many discussions, much further work to understand the theory behind it. And now, I think probably in reality, most people most codes would just quickly use the simplex method, but interior methods are definitely competitive. As always, this will be better in some problems, this will be better in other problems. Okay, so I've done everything except to explain the simplex method. And I haven't explained this interior point, sort of, there's a penalty. Anyway, there's a penalty as you get near the border, so it stops you short, and then you look again. I could try to explain that simplex method, since we've got to this point, in a few minutes. Can I take these few minutes to describe how the simplex method works? Oh! And I haven't done duality. I haven't looked at the, and this is, I want to do. I haven't looked at the dual problem. So what's the dual problem in this particular case? B is just the number 4, I think. There's only one y. And what's the constraint in the dual problem? A transpose y less or equals c. A was 1, 1, 2. So that's, now transpose is 1, 1, 2, 1, 1, 2, multiplying y is less than or equal to, what are the costs? 5, 3, and 8. Yeah, I'd rather tell you about the dual problem. Okay. Okay. So that says y less or equal 5, y less or equal 3, 2y less or equal 8. And what's the biggest y? Oh, you could tell me the answer. We could solve that dual problem. I want to maximize 4y, where y has to be less or equal 5, also less or equal 3, and 2y less or equal 8. So what's the smallest y? The largest y, yes, the largest y possible is, no, but the y has to solve all 3 of these conditions. So it's 3, right. The y has to be less or equal to 5. The y has to be less. Essentially, I have a cheater who's competing with the PhD for the money. But he has to also compete with the grad student for the money. And the grad student, because he's cheaper, the cheater has to reduce his rate because he has to beat the grad student. And he has to also beat what the computer is charging. So this cheater, if you allow me to use that word, is coming in and saying, I'll solve the problems for you. Pay me. And he's going to solve 4 problems, and he wants to set his rate as high as he can. But he can't set the rate above what he's competing with. And he's competing, among other things, with the grad student. So the cheater can't set his rate per problem. He charges a rate per problem, not per hour, because he's just looking up the answers. It only takes him 2 seconds. But per problem, he has to beat or match. Yeah, like auto sales here. He has to match what the other guys will do. And the other guys will solve so many. The computer solves charges $4 a problem, right? Because the computer charges $8 an hour but solves 2 problems. So the computer is really charging $4 a problem. So the cheater can't charge more than 4. But the grad student is only charging $3 a problem. So what's the minimum, the maximum here? What's the y star? The y star is, how much can the cheater charge? 3. The maximum is y equals 3. This is the tight constraint. And the maximum is 12. And that's what, of course, the grad student charged. He charged, it took the grad student 4 hours, where it only took the cheater 4 seconds, but the grad student, the cost was the same, so that this was 12 equal 12. And And we could even see that it was optimal. Do you see why it's optimal? Which of these inequalities, yeah, do you see why? You see the winning x star, you remember x star is 0, 4, 0, only the grad student works. So two components of x are 0, and in those two components, the cheater has inequalities. But in the component which matches the grad student, in x, the cheater has equalities. You see, it's just a beautiful subject. This complementarity of the two problems, and it gives this, because this is a theme through all of optimization. The best algorithms are called primal dual algorithms. They pay attention to both problems at once and solve faster. Okay, so we saw the dual problem there, and you saw how it came out of the blue. I mean, somebody was prepared to do the same job and wanted to maximum income from that, and but constrained by the inequality, the max equaled the min. So that's the duality in this example. I could, maybe I'll, since time's really up on this lecture, I don't know whether to describe. Maybe I'll start by maybe I'll just quickly describe how does the simplex method operate. Yeah, because I already have in words. So let me just repeat those words. How does the simplex method work? Okay, we're at a corner. Okay. Now you might think, it's natural to think, okay, I'm going to travel to another corner, and I've got two edges to choose from. And you might think, okay, the natural thing is figure out the other corners, their costs, and choose the lowest. That sounds totally reasonable, but it takes time. To figure out where this corner is means solving a system of equations. So the simplex method doesn't do that. It computes the sort of steepness of the descent. If we let the grad student in to work for an hour, how much will that reduce the cost? If we let the computer in to work for an hour, how much will that reduce the cost? We're figuring out not knowing the length of the edge, because we don't know where the next corner is. We're figuring out, we're doing local problem around this corner. We're looking for the steepest descent. That's the steepest descent is the first idea in minimization. Go downhill. Go downhill as steeply as possible. Now, it can happen, and it actually does here, that the steepest descent is actually along this edge, but the edge, so then you say, okay, I'll take that edge. So that's the decision which the simplex method makes. Which way is steepest? Once that tells us which corner that tells us which new guy is coming into the picture. Then it solves the system AX equals B to find out where that corner is. And it has, and somebody, it's because it's a corner, somebody has to stop working. Okay, so it travels along there. So there I've described the simplex method without giving you the algebra of how it does it, but we're talking linear equations here. It's at a corner. It's wondering, okay, which x shall I let in? Which shall be the entering variable? Okay, so it says I've got a choice of edges, and along each edge it can figure out locally what the reduction in cost would be if we let these in, say, for a unit amount. And then it chooses the one that looks the best, the steepest. But just as in steepest descent, that doesn't mean it's going to hit the winner. Because this one could be steepest but shorter, and it very likely is. That it doesn't mean the steepest one is probably not the right one, but it's downhill anyway. So you go downhill to this point, and then again you apply the simplex method. You look around here. Well, this way it's descending. This way it's not even descending. So of course the steepest is this way. Travel along here. So the cost is at every simplex step you've got linear equations to solve. So that's why the cost depends on the number of equations, and then it depends on the number of steps you take. And the point is that, of course, the cost here, which is significant, is still polynomial, right? We have only m equations here. So, but in reality, that's a significant part of the cost is solving those equations. And then how many steps it takes can be exponentially large, but in reality is not. So there's the simplex method for linear programming, and so that's the practical side. And the basic side tells us the winner's a corner, and at the winning corner, the max equals the min. That's sort of my shot at linear programming here. And what's to be remembered? Well, first of all, it's described more fully in the Applied Math book. So you could look there for details of the method and some more mention of the excitement which came with Karmarkar's ideas. I can remember going to a meeting in Boston, standing room only in a Boston hotel when he first announced his results.
Was he an MIT professor?
No. Where was he at that time? Then he actually did come to visit MIT for a year after that, but his courses were not successful. And so I'm sure he wasn't that happy because nobody wants to give a class with one person or something, and that's what it happened, I think. So then he went to AT&T. So he's been at AT&T quite a while, but my impression is perhaps he's left. That was quite a while ago, and I think probably he's moved on, but I'm not 100% sure. But that was at the time where the question was, could you patent this? I mean, you know, this meeting in the Boston hotel was the newspapers were all there and everything. It was big news, and that was at the time, first time when I think he did patent it. By, of course, you can't patent an algorithm, which is what the simplex method is, but somehow the lawyers created a way you could patent the apparatus which would execute the algorithm, which was, of course, just a computer. But now it's a standard thing that stuff gets patented, and this set that precedent. I don't know about things here at the lab, but in engineering, math guys we're not business enough to do it. But all my friends in the wavelet world patent algorithms. I mean, the companies involved patent those ideas, and it's now an established part of life. Well, I'll pick up again at 3:30 if you like. Okay, good. Thanks.